All right, so let's take a look at today's lesson. We're going to be looking at properties of trig functions. This block right up here, these domain and range, out of context, just sitting in this table, they really don't make a lot of sense. We will talk more about domain and range as we get into graphing. I think there's a question or so on the homework that talks about domain and range, you could just refer to this chart. You could just refer back to the chart. So that represents the domain and range of all six trig functions. The periodic nature of trig, let's just talk about that a little bit briefly. So what this tells us is that if I were to add 2 pi to any angle here, that it would generate the exact same thing as if I hadn't. So let's talk about that with reaction to the unit circle. So if I am like at this angle right here, and I add 2 pi to it, it takes me to the exact same angle. So there's really no change. That's why these are equivalent. These expressions are equal or equivalent to each other. For cosine, the period is 2 pi. Tangent is a little different. That tangent's period is pi. So just a brief little look into the future. So what does it mean by a period? So here's sine. This is just, so this first part from like here to here, this would be 1 period. Because afterwards, so that would be like 1 period. After this point right here, it just repeats itself. That's what they mean by periodic. There's 1 period where that's unique, and then all the others copy it. They're all the same. That's periodic in nature. And the reason that tangent is so strange is because it looks like this, and it repeats itself. It repeats itself every pi, not 2 pi. So that's just something to note. We're not going to be really in depth with that right now. It's just a concept to think about. Our fundamental trig identities. We've got reciprocal identities. Now, hopefully these identities, we will be memorizing them, because we utilize them in all kinds of contexts. So we've got that secant is the reciprocal for sine, so that means that secant would be identical to 1 over sine. Cosecant, secant, so cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and it just, I really wish the C's matched and the S's matched. I just really did. It would be so much easier, I think, if they had made cosecant go with cosine, so they match, but they don't. So that's what makes, I guess that's what makes me remember that they're reciprocals of each other, because, cosecant goes with sine and secant goes with cosine. Cotangent and tangent, those are reciprocals of each other. These down here, some textbooks call these quotient properties. Okay, quotient properties, because tangent is equivalent to a quotient of 2 different trig functions. Tangent is the same thing as sine over cosine, and cotangent, since they're reciprocals, is the same thing as cosine over sine. So these are some basic identities that you probably already know. And if you don't know, probably be quite easy to memorize. Yes, ma'am.
So we memorize the first 3 or the first 5?
Well, we will eventually memorize all of them.
Okay.
Yeah, all.
But for this upcoming test?
For the upcoming test, you're going to have a formula chart, so you don't need to memorize anything, but it needs to be in your memory work, because by the next one, it'll be expected that you're memorized. So why? Why would we memorize these things? Because when we use them, which we will, when we use them, if you don't have them in your head and you have to rely on a piece of paper, it's going to slow you down considerably. Your work is going to take like twice as long if you don't have them in your head. So it's really important that you start working on it to memorize them, because it's going to make your life easier. I promise. It will make your life easier. All right. So let's talk about the Pythagorean identities. The first one is the only one I have memorized. I have this one memorized. I know that sine squared plus cosine squared is 1. I know this. I have it memorized. The other two I generate. I actually generate them. So when I'm working on some, an assignment, what I would do is at the top of my page or at the top of my document, I would write in sine squared plus cosine squared equals 1. And then I would divide each side by sine squared. So sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. And 1 over sine squared is cosecant squared. And you can see that we just generated that one without having to memorize it. The reason this is helpful to me is I get mixed up on where the 1 goes and which one goes on the same side as the 1. That's just confusing to me. So I don't even bother trying to memorize it. I just memorize sine squared plus cosine squared is 1, and then I generate the other two. It just takes a few seconds. So let's generate the other one. So we would do sine squared plus cosine squared is 1. Now let's divide both sides by cosine squared. So sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared. And I just generated that one. So really it saves on your memory work if you would just memorize sine squared plus cosine squared is 1. Please note, I've been teaching this a really long time, and I know where the errors come in. So I try to warn you. The most common errors, students think that they can say sine plus cosine is 1, and those not being squared. That is not true. That is not true. These must be squared. They must be squared to work. Okay, they've got to be squared or it's not going to work. It only works when it's squared. Okay. So the last identities we're going to talk about today are even-odd identities. Now I'm going to take your memory back to Algebra 2. So let's think about the parent parabola. We looked at even and odd last year. Let me try the parent parabola. Okay. So this is y equals x squared. If you recall from last year, this is an even function. Why is this an even function? There are two ways to test it. One would be to look at the graph. Even functions are symmetrical about the y-axis, if you recall from last year. And also, if you, let's call this f of x equals. If you do f of negative x and you plug in a negative for the x, and I simplify it, I fix it up, and I get the same thing I started with, that is the significance of an even function, because you plug in a negative x and you simplify and you get the same thing you started with. That's even. The even trig function is cosine. Cosine is even. You can see that you plug in the negative x and you generate just an x. That means it's an even function. So cosine is even, and its reciprocal secant is also even. Secant is also even. Okay? All the other trig functions are odd. So you can see tangent is odd, because when you plug in a negative x, you don't get the same thing you started with. You get the opposite of what you started with. You get a negative tangent. Sine is odd. When you plug in a negative x, you don't get the same thing you started with. You get the opposite of what you started with. So that's just a little refresher on even and odd. Yes, ma'am?
Are cotangent and cosecant, are they both odd?
Yes, they're both odd. So we have 2 even trig functions and 4 odd. 2 even and 4 odd. The 2 even ones are cosine and secant. All the other 4 are odd. So that's something to remember, because these identities will come up. They're actually going to come up in your homework where you would need to use them in an application. So just something to keep in mind, and the difference between even and odd. Okay? Would you like to see an example of an odd function, or are we okay? Okay, I'm going for it then. So an odd function would be like f of x equals x cubed. You know, it looks like this. These are symmetrical about the origin. And if I do f of negative x, and I plug in a negative x and cube it, I get f of negative x is negative x cubed. So it has the exact same property as tangent. If you notice, if I plug in a negative x for tangent, the result is the opposite of what I started with. If I plug in a negative x for x cubed, the result is the opposite of what I started with. That is an odd function. Okay, so this one is odd. Okay, even and odd. That's a reminder from last year. Is everybody okay? Okay, so let's go ahead and start on our examples on the next page. This is some of it is a bit of a review. They want us to find the exact values. So let's, first of all, 17 pi over 4 is way too big. There's a bunch of rotations on there. We know that sine has a period of 2 pi. Okay, it's got a period of 2 pi. And I know that if I take 17 pi over 4 and I get rid of all the rotations, that's going to be helpful. But it's in fourths. So what I should really do is I should think about 8 pi over 4. That's what I should think about. So how many times could I take 8 out of 17? Twice, right? Because 8 and 8 is 16. So let's think about it that way. I could take 2 of the 8 pi over 4. So I could take 16 pi over 4 out. And that would leave me with 1 pi over 4. So what we're looking at is, what is sine of pi over 4? Sine of pi over 4 is going to have the identical value to sine of 17 pi over 4. We just pulled off the rotations. So let's get to our unit circle. Okay, we know the fourths, so the 45, 45, 90s. We know that's what they are. We know that this coordinate point for 45, 45, 90s is the same all the time, right? Which is, remember the number? Yes, ma'am?
Square root of 2.
Perfect, square root of 2 over 2. So square root of 2 over 2, square root of 2 over 2. Okay, we're in the first quadrant, so they're both positive. So if you recall, sine is mapped to the y. So my answer is going to be the y coordinate. So it's just going to be root 2 over 2. It's kind of continuing to review for us from previous lessons. Are we okay? Okay. So let's work on the next one, 5 pi. It's got too many rotations on it again. So 5 pi tangent has a period of pi. Okay. So I could take off 4 pi's, right? Are y'all okay with that? I could take off 4 of those, and that would leave me tangent of pi. Okay, so that's right here. Okay, so recall tangent is mapped to a y over an x. So let's write this coordinate point. Do I have a volunteer to tell me what this coordinate point is? Yes, ma'am. Negative 1, 0. Good. Negative 1, 0. So we would take the y coordinate, which is 0, and put it over the x coordinate, which is negative 1. So that would end up simplifying to be what? 0. Just 0, right? 0 over negative 1 is just simply 0. Okay, that's our very first one. Are we okay? All right, let's go to number 2. So here we're looking at big picture things. Okay, big picture things, quadrants. They're giving us some information, and let's highlight this one. This one is yellow. Okay, sine. What we want to do is highlight the quadrants. Which quadrants would sine is mapped to a y. Which quadrants would y or sine be negative in? 1, 2, 3, 4? What do we think? The bottom ones, right? 3 and 4, the bottom ones. So I'm going to highlight. That's what this is. That is where that would be true. That would be true in quadrant 3 and 4. But we also, so this is in this problem where what they're asking us to do is figure out the quadrant where both of these things are true. We want both of them to be true. All right, so let's move, this will be blue. So we want to see where is cosine, and cosine is mapped to an x. Where would cosine be negative? Which quadrants would cosine be negative in? What do we got? Yes, ma'am, 2 and 3. That's exactly right. So 2 and 3. So our answer is going to be where those overlap. That's the answer, where both of those things are true. Both of those things are true in quadrant 3. And so that's our answer, is quadrant 3. Okay? Good, good. We're doing well. Let's go to number 3. Find the exact values of the 4 remaining trig functions using identities if. Okay. Well, we know this is pretty straightforward for us because we know that the reciprocal of sine is cosecant. And all I need to do is flip this upside down. Remember, we did some of that last time. So, and we don't need to rationalize. You really don't need to rationalize. The reciprocal of cosine is secant. And flipping that upside down. Now, if we want to write the identity out, which they're really asking us to use the identity, which we did, but let's be more specific. So we can say that cosecant is 1 over sine. That's what we did, right? We flipped it upside down. And secant is 1 over cosine. That's the formal identity that we use to get those answers. So far we've got 1, 2. We need the 2 more. So, okay, so let's think about tangent. So tangent is sine over cosine. Okay, so what could we do? We could do sine, which is root 5 over 5, over cosine, which is 2 root 5 over 5. And we'll refer back to our middle school days where when we were dividing, we would rather multiply the keep, change, flip, keep the top, change division to multiplication, and flip the bottom. Hopefully we can see that this root 5 will cancel with that root 5. And this 5 will cancel with this 5. So what we end up being left with is that tangent of theta is 1/2. Since we know tangent of theta, we know that cotangent of theta is 1 over tangent. So cotangent of theta would be 2. Okay, so we accomplished everything they asked us to. We found all 4 exact values, and we used all the identities. We wrote the identities out. You'd probably get some credit for writing the identity and then credit for having the correct answer, okay? Because it specifically said using identities. Okay, is everybody all right? Okay, let's move to number 4. Now this one is kind of interesting. Well, in a little bit of a crazy way. I want to focus on this. This looks like a big mess right there. I'm going to leave that alone for a second. We'll just copy down sine squared pi over 12. I don't really want to mess with that yet, but 1 over secant squared, that's an identity, right? 1 over, so if I did 1 over secant squared, I would get, what's the reciprocal of secant? Cosine. I would get cosine squared. So why don't we rewrite this one? Let's just rewrite it as, instead of 1 over secant squared, let's write it as cosine squared. Now, let's think about that. I've got sine squared pi over 12 plus cosine squared pi over 12. Does that ring any bells from what we just looked at? It does, doesn't it? What about sine squared x plus cosine squared x? It's 1, right? So those, now this would not work if pi over 12 was not identical in both of them. See how they both have an angle measure of pi over 12? So this is totally equal to 1. My final answer would be 1 because these two right here must match. They must match to be able to achieve an answer of 1. Now you have some homework problems that do some crazy things like that, where your answer is going to be like 1 or 0 or -1 when they make you use identities like this. That's why I put this one in here. Okay, so you can kind of get a feel for what you're going to be seeing. All right, let's take a look at number 5. On this one, spacing went a little crazy. If you would, these should not be. This should be there should be a space right there, and I missed that space. If you would just kind of mark a space in there for me, I'm gonna have to go back and fix that. But it shouldn't be like that. It should be, there should be a space. So what they want us to do is find the exact value of the remaining trig functions. Well, okay, we can deal with sine being 1/3. All right, we got that. But what are we going to do about cosine being negative? Let's think about the coordinate plane. So I need cosine to be negative, but I need sine to be positive. Where is that going to be? Which quadrant would sine be positive and cosine be negative? The second quadrant. So I'm going to draw my triangle. This should be a review from the other day. I'm going to draw my triangle in the second quadrant. We know sine is opposite over hypotenuse, so I can put 2 sides of my triangle. Then we resort to Pythagorean theorem to find the third. So 1 squared plus b squared equals 3 squared. B squared is 9 minus 1, or 8. So b needs to be a plus or minus 2 root 2. The square root of 8 reduces to 2 root 2. Now, which one of those would we use? We need to be specific to the quadrant that we're in. We're in the second quadrant. We're going to use the negative. We're going to use negative 2 root 2 as our side measure of that triangle. So now we have everything that we need to finish this problem. We're going to find, so we already have sine, so let's do its reciprocal, which is cosecant. We just flip that upside down and we get a 3. All right, so let's start on the other. So we've got cosine and its reciprocal, which is secant. We've got tangent and its reciprocal, which is cotangent. Okay, so we're going to go through, just read those values off the triangle using our SOHCAHTOA knowledge from, years ago. So cosine we know is adjacent over hypotenuse. And we just flip it upside down for secant. Again, we don't need to worry about rationalizing. Don't worry about rationalizing. Tangent is TOA, SOHCAHTOA, opposite over adjacent. So 1 over negative 2 root 2. And cotangent, we just flip it right upside down. Negative 1 over 2 root 2. Oops, I'm so goofy. Negative 2 root 2 over 1 is just negative 2 root 2. And there's our other 5 trig functions. Okay. Are we comfortable? Okay. Last one, we're going to look at even-odd properties. They want us to find the exact value using even-odd properties. I mean, even if they didn't want us to use even-odd properties, we could, right? So we know cosine is even, so this is going to be exactly the same as cosine of pi. These are going to be identical. So let's get our unit circle out. Pi is right here. We just talked about those coordinate points just a few minutes ago. And cosine is mapped to what, x or y? X. Cosine is mapped to x. So the answer to this problem would be -1. Very nice. Okay. Tangent is odd. So this is going to be the same thing as negative tangent of 37 pi over 4. Okay, 37 pi over 4, that's way too big for me. We need to pull out some stuff. So 2 pi in this case, we're going to make it 8 pi over 4. Okay, so let's think about this for a minute. So how many 8s could we take out of 37? Can we take 4 out? Right, 4. So let's just do some scratch work. So 37 pi over 4 minus, what, 32 pi over 4? That would give us, is that 5 pi over 4? Are we good? Okay. So let's do our unit circle. I'm going to count the fourths. I'm going to count like a round. So 1 pi over 4. I usually put dots when I'm counting just so I keep track. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. So 5 is right here. All right, good. So tangent is mapped to a y over x. So we need both coordinate points. I think we talked earlier about all 45, 45, 90s are the root 2 over 2, root 2 over 2, right? But what are our signs down here? Yes, they're both negative. They are both negative. So when I put the y value over the x value, what is that going to generate for me? A 1. That's going to generate for me a 1. So this part of my problem right here is 1, and then this part I would need to bring down would make it negative. So my final answer would be -1. Okay, how are we doing? All right.